we talked about a bomb calorimeter. This is something much less fancy, a coffee cup calorimeter. And it literally is made out of styrofoam coffee cups. And when we do experiment 7B, we're going to use coffee cups and do something like this. So here we have 2 nested styrofoam cups. We're using 2 just for better insulation. We want all of the heat exchange that happens inside of there to stay inside the cup and not leave. Here's a cork lid that's loose fitting. We're going to use cardboard that's older than you are. Squares of cardboard. They're like antiques now. We need to stir it some way here, a glass rod instead of a fancy thing, and just a plain old glass thermometer here to record the temperature. So this is happening at constant pressure. Q solution, these are going to be aqueous solutions. So we've got this solution inside the coffee cup, and that's what we can measure. We can measure the mass of the solution. We can measure the specific heat capacity of the solution. We can measure the change in temperature of the solution. Q reaction, where did the solution get its energy from? From the chemical reaction that was occurring. It's the same amount of energy, it's just that the sign is different. If one loses, the other gains. So we can say that Q reaction is equal to Q at constant pressure, which is the heat of reaction. Delta H is usually expressed in joules or kilojoules per mole. And so what we're going to do to get that per mole, like we did in the previous example, is we're going to figure out how much stuff reacted and convert that to moles and just divide the energy by the moles. So here's an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate the heat of reaction as written. For the reaction as written, use 1 gram per milliliter as the density of the solution, and C sub S equals 4.18 joules per gram degree Celsius as the specific heat capacity. Yikes. We read the whole thing. Now I'm going to highlight the numbers. This kind of makes them jump out at us. There's a whole bunch of numbers in this one. And then what are we trying to find? Trying to find delta H. So we just discussed that delta H is equal to the Q at constant pressure, and that is equal to negative Q for the solution. Well, what's Q for the solution? MC delta T. Q equals MC delta T. It's the mass of the solution times the specific heat capacity of the solution times the change in temperature of the solution. SOLN is an abbreviation for solution. So if we think about what equations relate to this, it can help us as we try to identify what these numbers are. So we've got 50 milliliters of 0.1 molar and 50 milliliters of 0.1 molar, and does that appear to have any impact on this at all? It doesn't, does it? So maybe we'll just skip those, and maybe we'll need them later. So I'm going to start here with temperatures, because that's going to be how I'm going to get my delta T, right? And I have a limited amount of space down here. So 23.40 degrees Celsius. What kind of a temperature is that, initial or final? initial. That's where it starts. And T final is the one it goes to, which is 24.21 degrees Celsius. And then they're giving me the specific heat capacity for the solution of 4.18 joules per gram degree Celsius. Because there was this density, but there's no density up there. What's with that? So we're trying to find Q for the solution. That's going to be the mass of the solution times the specific heat capacity of the solution times the change in temperature of the solution, and I'm realizing I wrote that all up there. Well, so this is C, and we can find delta T, right? Delta T is the final 24.21 minus the initial 23.40. Put it down here. 0.81. So I've got this guy and this guy, but I'm missing the mass. So maybe those numbers we kind of skipped over. And, you know, a problem like this, seeing it for the first time, this is critical thinking, because you're like, but wait, I've never done a problem like this before. What do I do? Well, you pull together things that you learn from other problems, and you have to put them together. We have 50 milliliters of this and 50 milliliters of that, and we have a density, and we're trying to find a mass. If we knew what the volume of the solution was, we have the density, we can calculate the mass. So what's the volume of solution? It's 100. It's 50 plus 50, right? So we've got 50 plus 50, so that's going to be 100.0 milliliters. 100.0 milliliters, and I want to change that into grams. I'm going to divide by milliliters. Use density as a conversion factor. Well, my density is 1 gram per milliliter. 1.00 grams per milliliter. So then I've got 100 grams of solution. There's the mass I was missing. Okay, so I have 100 grams times the specific heat capacity times the change in temperature. So 100 times 4.18 times 0.18 is 338.58 joules, with 2 sig figs because of this temperature here. Okay, so that is Q for the solution. So Q for the reaction is negative Q solution, which would be negative 338.58 joules. But it wants delta H for the reaction as written. So if we're going to put a delta H out here, delta H equals, this value has to relate to 1 mole of silver nitrate and 1 mole of HCl. Is that what we have in our calorimeter? Well, we need to figure that out, right? So we have 50 milliliters So if we convert that to liters, or actually let's just do it like this, 50 milliliters is 50 times 10 to the minus 3 liters. And then we have our molarity, 0.1 moles per liter. It's going to give me 0.005. I need to throw in some zeros in there because I still have 3 sig figs. So this tells me how many moles of silver nitrate. It's the 50 milliliters times the 0.1 molar. Well, they also gave me information about this other one. I've got information about 2, so this could be a limiting reactant problem. Heaven help us. So we have to look at that too. But look, the volume is the same, and the molarity is the same. That means the moles are the same, right? So we've got 0.005 moles of that and 0.005 moles of that. They are the same. So we could use either of them. I'm going to use 0.005. Which one is that? It doesn't matter. They're the same. So I'm going to take this and divide by the amount of stuff that actually reacted. So I take my negative 338.58, divide by 0.005, negative 67716 joules per mole. But 2 sig figs. So if you set, well, let's convert this to kilojoules, right? So that's negative 67.716 kilojoules per mole. It's just a more appropriate size of unit. And then that's going to be negative 68 kilojoules per mole. So up here, heat of reaction is negative 68 kilojoules. We don't write the per mole part here because it's understood. This is per 1 mole of that, per 1 mole of that, per 1 mole of that, per 1 mole of that. Any questions? I'm going to skip that one because I don't like it.